Okay. Well, hello everyone, and we've just gone past 2 o'clock, so I think we'll start kicking things off. Welcome to the first seminar of the term, new Influence term, and we're lucky to have Andrea presenting for us this term. Just to let you all know, we are recording, so questions, comments, all recorded. We do make this available to anyone who requests that can't be here in person. And so yes, just to be aware of that, but I will hand over to Andrea.
Thank you, Susan. So good afternoon, everybody. I'm a DPhil student here at Geography and also at INET at the Complexity and Economics of Sustainability Center, as well as the Smith School. So today I will present some joint work with Pablo Austiri, US Savets, from the title Reconstructing from Level Input-Output Tables from, or networks actually, from partial information, inferring link weights and assessing shock propagation. So, okay, maybe I need to click to, sorry. Okay, yeah. So the agenda for today is that I will give you some motivation of why this work matters. Then I will go over the data that we use and the methods, discuss the results and draw some conclusions. The war in Ukraine and the COVID pandemic have made clear that shocks to supply chains are localized geographically or firm specific, but however, they have repercussions on the global economy. Shocks of such type are going to just be increasing both in frequency and severity due to climate change. So it is imperative that we model the macroeconomy from the bottom up, and especially at the firm level, and also taking into account of supply chain relations. So what data is available? Well, data on firm level production networks are scarce and often incomplete. Here you see 3 examples, which I have divided by the breadth of coverage. So industrial data set, one industry, either in one country or globally. National data sets, of course, the economy of one country, for instance, Belgium or Brazil or Ecuador. And then global data sets, which is really what we would be after. And indeed, we use one of these data sets for our work. However, this data set mostly cover publicly listed firms and also meets a lot of links. What I wanted to focus on is this column weighted, and I will explain in a second what I mean by that. But just notice that most networks are not weighted. So what do I mean by that? So, of course, most networks have the binary topology. So we know, for instance, that for firm 1 has 2 customers. What we would like to know, however, are the money flows. So we would like to know, for instance, that firm 1 sells $30 worth of output to firm 2 and $2 worth of output to firm 3. So the research question is whether we can reconstruct these money flows, given that we know the binary topology, although partially, and also we usually have access to aggregate information for each firm from their financial statements. There is some previous research on this, and it mostly deals with financial or trade networks or input-output tables at the sector level. There are a few studies on firm level networks, which are all listed here, but all of them except one, and that is Yalongo and co-authors, they do not assess the quality of the reconstruction method, and that is because they lack the ground truth network. So we employ 2 data sets in our work. So one is the FactSet data set, which is the global supply chain network I was discussing before. But we don't know the weights. So we test our reconstruction methods using the administrative data set of Ecuador. From FactSet, we use 2 pieces of information, so the supply chain relations and the financial statements.
Andrea, is that a real supply chain now?
So this is the FactSet network. Is not all the firm. Is just, I don't remember if it's, yeah, I don't remember how many, but it was too many for the image otherwise. Yeah.
That's pretty cool.
So how does FactSet collect the supply chain relations? So mostly come from annual filings. So firms listed on US stock exchanges have to disclose their major customers, where a major customer is a customer that accounts for 10% or more of a firm annual revenues. And this is the main source. So there is a bias in the kind of links that we are observing, but also in the types of firms that are in the data sets, which are mostly listed firms. Also, some private firms disclose their financial statements. Then they recover more supply chain relations from, for instance, investor presentation, press releases. So we merge this data set with shipment level data sets that also is available through FactSet, and it only collects shipment from and to US ports.
How about suppliers? Do they list suppliers?
No, just the customer. So you recover, the network by.
Well, if the suppliers are in the.
Yeah. Here we are comparing the sectoral composition of FactSet in green and the word input output data, FactSet in green and the word input output database in gray, which is based on national accounts. We use the 2014 network, so we exclude firms in finance and insurance and public administration and defense. So there is some deviation in the sectoral composition, which is given by gross output shares, by the way, on the y-axis, between the FactSet data set and a data set based on national accounts.
So just to make sure I understand, when you did this reconstruction, because you're missing a lot of stuff in FactSet, well, I guess you have all the firms. Sorry, you're missing a lot of the links, but so in the green, you add up what FactSet says, which if it has enough companies, I would have thought it would be less because it's missing things.
So this is the share. So basically it's the sum of the revenues of firms in manufacturing divided by the revenues of all the firms in the data set.
Yeah, so just it's a sectoral composition.
Yeah.
I see. Okay, it's just a relative.
It's clearly missing some sectors. Yeah.
Fine. Right.
Yeah.
Okay. Good.
So how much of gross output do we capture with the data set? Of course, this is cleaned. So we capture around 26% of world gross output. So what we do for the analysis, and it will become clearer later, we introduce a synthetic node or a proxy sector to capture the rest of the economy. And we use the word input output database to do so. The Ecuador data set, on the other hand, is an administrative data set collected through VAT filings. It covers all legal and natural persons in the country and the relationships among them aggregated per year. So a legal person is simply a firm. A natural person is any person that carries out an economic activity. We know the sectors that they are in, but we do not have access to financial statements. So to impute some key variables, we use input-output tables. And we use also for Ecuador the 2014 network. Here are some summary statistics of the FactSet network at the top and Ecuador network at the bottom. So this is the full network, legal and natural persons, and this is the network of only firms. However, we use a test network. And this is because since FactSet is missing a lot of firms and links, if we had used either of these two networks, we would have got better results for our reconstruction that it would actually be in the FactSet case. So we keep the biggest firms, since we have publicly listed firms in FactSet. We match the number of firms in FactSet. So in FactSet, there are around 11,000 firms. So nodes in this case are the firms. Well, four are missing here just because they didn't have any other links with the firms that we kept. So, but it doesn't change much. So What stands out is that the test network is way denser than the FactSet network. So it has way around 1 million supply chain relations. On the other hand, FactSet at only 66,000. Yeah.
A quick question. How did you choose which 11,000 in Ecuador again? Just the 11,000 biggest?
The biggest, yeah.
So they could be from different, like the sector distribution could be different from FactSet.
Yeah. So I have a slide also about that. Yeah.
But you constructed links at random somehow?
So these are the actual links among the biggest 11,479 firms. There are actually 1 million.
Right.
So what we do then, because then it would, because it's an administrative data set, so it has more links.
But there's no 10% threshold.
No, there is actually no threshold in the Ecuadorian data set. So you see like super small money flows as well in the network.
The density, so.
Yeah, so what we do then next is to delete links at random, and we delete links that have a small weight with a higher probability to match the density of FactSet. And we do this randomized procedure 50 times. Here is just to recap how we reconstructed, but what stands out is that doing this deletion procedure, basically 93% of the links in the Ecuadorian data sets are deleted. So what, I will now go over the method. First of all, I have a toil example to make clear what we are actually doing. So in this economy, there are 4 firms. On the columns, there are the suppliers of a firm. So firm 2 buys some of its input from firm 1 and firm 4 for total intermediate costs of 20. On the rows, you can see the customers. So firm 2 sells some of its output to firm 1, firm 3, and firm 4 for total intermediate sales of $25. What we would ultimately like to do is to reconstruct the money flows. So we would want to know that firm 2 actually sells $5 worth of output to firm 1, $15 worth of output from firm 3, and $5 worth of output from firm 4 for total intermediate sales of 25. Because I was telling that FactSet doesn't capture the whole economy, we also add a proxy node. There will be another column here and here that is linked to all the firms, both incoming and outgoing links. We take a method off the shelf developed by Parisi and co-author, and it's a conditional maximum entropy method. So what it does is that it maximizes the entropy S of all the possible weighted networks configurations, given all the possible binary topologies. So it's an ensemble method. It generates an ensemble of networks. Of course, we specify a deterministic structure for the binary topology, but in theory, one could use a link prediction algorithm and then account for the uncertainty in the prediction of the links. We impose 2 constraints. So one is just a normalization condition for the density. And the second one is on the expected weight. So it meets the constraints in expectation. Of course, we don't know the expected weight. So we derive the expected weight from a previous step, which I will describe in a second, where we impose constraints on what we know, which are the intermediate sales and costs. This has 2 benefits. First of all, it speeds up the computation. And second of all, the authors have shown that doing so, instead of just putting directly constraints on intermediate sales and costs, produces a better reconstruction of the weights. So in the first step, it's still a maximum entropy problem, but in this case, it's deterministic. And it's an entropy-like functional because here the entropy function is in terms of raw weights and usually it's in terms of probabilities. And we put constraints on intermediate sales, so SI out star, which we know, and on intermediate costs of each firm, SJ star. And then we get a solution where the weight is a function of the total intermediate sales of the supplier and total intermediate cost of the customer, normalized by the total weight of the network. And those of you that are familiar with a gravity model, you might recognize that this is a gravity model without distance. So if we go back to this problem and we solve the problem, we find that the density Qij of the weight, given that there is a link, is of exponential form with parameter lambda ij, which is the Lagrange multiplier. Then one proceeds on setting up the generalized likelihood function for a given set of constraint, g of lambda. And solving for the first order condition, we found that the expected weight is given by the ratio of the probability of a link between I and j and the Lagrange multiplier. And this needs to be equal to the maximum entropy solution, the deterministic one. And then we can find a solution for the Lagrange multiplier and for the weight.
But here you need to make you need to decide how much you attribute to the missing node.
Basically the missing node we constructed with the aid of the word input output database. So basically we sum the intermediate cost or sales of the firm, and then we take the difference, the intermediate cost of the word input output database minus those observed.
So the word input output is also firm level?
It's sector level data.
So you assume all firms in a sector have
we have
fraction of...
So we have to discharge the country and sector dimension because of problems in reconciling national accounts with financial accounts at the firm level, unfortunately, yes.
So then you apply the same fraction of missing sales to each firm in the sector, is that the
So basically what you have is that you have in the matrix that I was showing you before, let's see, you have an extra column and row. So you have an extra column and row, which would say proxy sector. And then you have ones, basically, all columns and all the column and the row of the proxy sector are all ones. And then you put as constraint this difference that I was telling you from the total intermediate sales at the word level minus the intermediate sales of firms. And then you put the constraint for the proxy node.
So would it be a correct interpretation to say the proxy sector is like a giant firm connected to everything? That's it?
Exactly.
Still, I don't understand the detail because the world input output data is the whole world. Your sample is the sub-sample. You need to scale something. For example, you said it's 26% about and multiply the world number by 26% and then put it there.
No, so it's 26% of word gross output compared to the word input output database. And the word input output database is in dollars and FactSet is in dollars. So you just need to subtract the two without doing any adjustment. Still not.
Accounts for like 74%.
Okay, so we are, okay. So of course, what I've been discussing so far captures just one part of the economic activity, and namely the firms to firm trades. What we would also want to capture are other actors in the economy, and namely final consumption, and also the value added by labor and capital for each firm. So we proceed on reconstructing this outside of the maximum entropy procedure. Final demand is basically impossible to observe at the firm level. So we infer it with the aid of input-output tables at the sector level. So here it's final demand of firm I, and these are the revenues of firm I. And basically we assume that firm I satisfied the same proportion of final demand as the sector that she's in. So here it's final demand of sector S, and gross output of sector S. For value added, it's the sum of labor cost or wages, capital expenditure, and profits. The tricky part to estimate is labor costs, because depending on how firms choose to write their financial statement, they can either disclose it or not. And if they don't, they might bundle it together with intermediate costs. So we use what we know for some of the firm, and we try to predict it for the other firms, and then we clean the cost of goods sold. We assess the reconstruction at two levels. So one is the micro scale and the other one the macro scale. So at the micro scale, we use weights, technical, and allocation coefficients, which I will explain in a second. And the macro scale, we divide it into two. So we assess demand side shocks and supply side shocks. For demand side shocks, we look at the output multipliers, and then we use a simple input-output model to predict the revenues growth rates with the reconstructed network and compare it if we use the true one. The same for supply side shocks, we look at the influence vector, and then we use another standard input-output model to predict aggregate volatility. So the technical and allocation coefficients are basically just a renormalization of the weighted adjacency matrix. And so the technical coefficient normalizes the weight column-wise. So a link goes from I to J, and the money flows from J to I. So we divide the weight by the total intermediate costs of firm J, the customer, plus value added, YJ. And so the technical coefficients give us the percentage of input that firm J buys from firm I. Similarly, the allocation coefficient normalizes the weighted adjacency matrix row-wise. So we have that the weight is divided by the total intermediate sales of the supplier plus the final demand satisfied by I. So this gives us the percentage of output that firm I sells to firm J. So moving on to demand side shocks, we use the input-output inoperability model, which starts from the basic accounting equation stating that revenues are equal to total intermediate sales price plus final demand. Then we substitute for the technical coefficient, and rearranging, we arrive at the Leontief model, where L is the Leontief inverse, and it's the total requirement matrix, and it encapsulates basically the supply chain structure and connections. We further take growth rates. So this is the growth rates of firm revenues. And F is the change in final demand from T-1 to T relative to revenues at T-1. So we know basically what we will do is that we use F star, which we know, and then we will use either the Leontief inverse with the reconstructed network or the empirical one to predict the revenues. The output multipliers are a centrality measure, and they capture the upstream propagation channel of an exogenous shock to final demand, and then its economy-wide impacts. It can also be seen as an upstream measure. So the bigger the multiplier is, the more downstream. The more downstream a firm is with respect to the primary input suppliers, so capital and labor. And therefore, it can also be seen as the average length of a firm production chains. So the higher the output multiplier, the bigger the impacts of a shock to the wider economy. For supply side, we also use a standard input-output model. So it has Cobb-Douglas technologies. I didn't list all the assumptions here, but it's a standard economic model. If you want to know more, ask me. But we use two extensions proposed by Magerman and co-author. Basically, we allow for monopolistic competition and heterogeneous labor and final demand shares. And so if you solve the model in equilibrium, the firm revenues are given by this equation, where basically here the inverse is basically just a Leontief inverse. So omega is the matrix of input share. So yet another renormalization of the weighted adjacency matrix, which just takes into account total costs, total intermediate costs and not value added. Alpha is the labor share. So basically revenues are a function of the total, the network structure, the intermediate input share, 1 minus alpha, and final demand. From that equation, we can derive the influence vector, yet another centrality measure that measures the importance of firms in aggregate output. Basically here, yeah, the labor share, and here we have the final demand shares, which if you are familiar with the work of Acemoglu, which were the first to propose the model, basically if you have homogeneous demand share and homogeneous labor share, you recover their influence vector. You can then derive an equation for aggregate volatility. So this is the standard deviation of the growth rate of aggregate GDP. VU is the influence vector that we've seen so far, and delta epsilon IT are TFP shocks. So we model supply shocks as shock to total factor productivity, which are assumed to be IID with mean zero and bounded variance. I will now show you some results. So these are the weights of Ecuador. Here we see the empirical value on the x-axis and the expected value on the y-axis. So we see that they're kind of fairly scattered around the identity line, but there is quite a spread at mid values. And indeed, not surprisingly, what maximum entropy does is that it underpredicts high weights with high values and overpredicts weights with smaller values. So it tends to produce a distribution which is more homogeneous. So here is the complementary cumulative distribution function of the empirical in black and expected in red. We fit also a power law distribution. And so we can also quite recover the exponent, and especially they both imply divergent second moment. So the empirical is 1.1 and the expected is 1.3. And the fact that it tends to reconstruct a distribution which is more homogeneous can also be seen from the entropy, which here we compare it with an entropy of a uniform distribution. So if it's 1, then it's basically a uniform distribution.
So on the picture on the left, it appears that for the larger weights, you're doing a better job. Now, but that could just be because you have fewer larger weights, so the cloud is not as big. Is it the case that you do better for large weights?
So
It would be nice if you did, because those are the ones you really care about.
So I did, if I remember correctly, because I did a plot of the empirical weights against the error term. So you get a bigger error term for the higher the weight.
It's going to be a bigger in absolute value.
In absolute value,
but
yeah.
Relative. If you're getting it smaller in relative value, that's really a major benefit, because you're getting huge errors in some of the small weights there, right? You're off in many cases by an order of magnitude.
It's a log scale.
Yeah, it's a log scale. Yeah.
Well, even so, it's showing that you're off by an order of magnitude or more, right? Yeah, or even 2 orders of magnitude. So for the small ones, you're doing, in some cases, really quite badly. But for the larger ones, it's looking better. So, but it may be that it's just because there are fewer large weights, so you just don't see as much.
Yeah, so there are fewer indeed.
Yeah. But so I guess you should really look at that.
Yeah, thank you.
But that's always the case with maximum entropy, because the large weights, you can tweak them a lot. They basically bind the constraint. Whereas the small weights, you can play around. They don't really.
Yeah, exactly. So here we see the same plots for the technical coefficient in the upper row and the allocation coefficient. Here they're more spread around the identity line. And again, maximum entropy tends to reproduce a more uniform distribution.
And yeah, it would be better if you did logs because everything's bunched in the corner, so it's hard to tell.
So these are computed from the previous graph, right?
Yeah, so it's just a renormalization of, well, here are some, let's see how I do it. Okay, maybe I'm gonna skip this. So here we see the same for FactSet, which we don't know, of course, the ground truth, but we can, this is the weight, technical, and allocation coefficient. So we can still recover a power law exponent that implies infinite second moments, although it's higher. What is worrying here is the allocation coefficient. So the allocation coefficients are connected to the major customer threshold. The major customer is a customer that sells 10% of more of a firm's annual sales, and this is exactly what the allocation coefficient is capturing. So I was expecting to see most of the mass of the distribution to be centered around 10%, whereas 10% is not even in the distribution in the ranges, and this is because of the many data imputation procedure. And how the proxy sector is constructed. Basically, if you look at both the allocation and the technical coefficients that the firms have with the proxy sector, they mostly sell and buy from the proxy sector.
So it means that most of the things are not in the data set.
Yeah.
It's dark matter.
Yeah.
About the same ratios too.
So we do a better job to reconstruct the output multiplier and the influence vector. We tend to overestimate the influence vector and underestimate the output multipliers. We match quite well the distributions.
Sorry to interrupt. Do there seem to be some correlations between which firms you're able to construct well for? Like, is it certain sectors of firms that you do well with, certain sectors where you don't? Is this something you've looked at?
Yeah, I have. Wait,
I'm sorry to make you skip it.
Yeah, no, I actually have it. I don't dare to exit the full mode. So, but I have a slide in the appendix that looks at exactly that. Yeah, so here is the output multiplier by sector. So you can see that like it's really clustered, but I'm not sure where there is like a sector that is better, because this is, maybe. And similarly, oops, where did I put it? Yeah, similarly here, maybe, for the influence vector, maybe this red stars, so human health and social work activities, seems to be slightly better.
Okay, so yours, I think the previous graph, not this one, the previous one, the sector one,
This one.
So this means that more or less, except for the green and blue, the weights are also in the correct blocks in the matrix.
The weights are in the correct blocks,
Which is not obvious from the distribution.
Yeah.
This is much more informative.
Maybe I should have put this one as the next slide.
But there's no sector constraint in the reconstruction.
No, there is no sectoral constraints, because we do not know that from financial accounts. So we didn't put any constraints because for information that we didn't have. Okay, so these are the multipliers for FactSet. What we can say about the reconstruction is with regard to the influence vector here, this is the output multiplier again. So if you fit a power law distribution to the influence vector, we get an exponent which is 1.2, which is the same, which is equal to what Magerman and co-authors find for Belgium. And we also find similar results for Hungary and the full Ecuadorian network.
Sorry, just a question. When you compute the multipliers, are you leaving the external node, the synthetic node, inside or outside of the network?
No, I'm keeping it in the computation because I want to like have also that propagation channel captured.
Okay.
Yeah.
Do you think that makes, because I guess that must have a big impact on the value of the multipliers now, because essentially you put a node that makes each firm very close to any other one, because every firm is at distance 2 of any other firm in the network.
Yeah,
Right?
so it doesn't change much, right, with regard to the others, because how I'm calculating the empirical ones is that I'm taking the full network of firms, I'm calculating the influence vector for them, whereas for the empirical one, I'm using the proxy node. So we actually do a good job, even with the proxy node in the calculation. What is the only difference is that like the proxy node, and we will see later, has a massive centrality measure, basically. Okay, so now we look at the growth rates of firm revenues. So here it's just to remind you of like the model that we're using. And so again, as before, the empirical on the X and the predicted on the Y axis. So at first sight, you can see that for FactSet is way worse, but that's because there is a key difference. So for Ecuador, we don't know we don't know the revenues. So what we do is that we use input-output tables to reconstruct F star, and then we use the empirical or reconstructed network to predict either the empirical or the predictor revenue growth rate using the reconstructed network. So what you see here, the error term is really due just to the differences in the structure of the reconstructed network and the empirical one. Whereas for FactSet, what we do is that we take revenues from financial accounts. So in there is also model misspecification basically in the error term in predicting the revenues. Nevertheless, like we can predict for 90% of the firms, more or less, a correct sign of the revenues growth rates. For aggregate volatility, yeah.
Andrea, could you say a little bit, why do you get these stripes in the FactSet?
Oh yeah.
A lot of lines. What are the lines?
So I have a slide also in the. So this is for the imputation of final demand using sector level data. So like what we saw before for Ecuador, like if you color it by sector, you can really see each sector.
So each line is a sector.
Yeah, yeah.
Okay.
And the same, like here, you would see clusters corresponding to sectors.
But okay,
Is that an artifact of the assumption on how you're calculating final demand?
Yeah, because for each firm in each sector, we use the same ratio.
The same ratio.
Yeah.
But it says that also says that some you do reasonably well, right? Others you're doing very poorly because you have some of those lines that are almost horizontal.
Yeah.
Right. And so why is it that the error is so sector specific? That is the slope of the line, you know, when it's close to 1, then you're doing well. So sorry, maybe you should just point. This sector right here, you do pretty well for. This sector right here, you're doing terribly.
Yeah.
Because this is a actual versus predicted. Right?
Yeah. But so the sector is on the diagonal line. So maybe do you want to see maybe the picture?
No, but I'm asking why are the slopes of those lines so different? Right? Why is it that each sector has a slope and some of the slopes are way off and some of the slopes are not bad?
It's something I need to investigate more. But for instance, like this firm for which we do very bad is like a Chinese firm in either IT or the automotive industry. So I guess that like maybe some sectors grew more, and then maybe we have with respect to others, like some sectors dynamics, I guess.
Well, it does suggest if those lines are sectors, if you can understand why the slope is off, you might be able to figure out a way to correct that.
Yeah, and it's even more peculiar because they're linear. So it
Yeah.
seems that you're missing the growth rate by a factor,
Yeah.
which is the same for all sectors. So I think it would be linked to the way you put the attribute the fraction to the missing node.
Yeah.
That scales up everything up or down by some factor. So if you don't scale that correctly,
Yeah. Thank you.
so for example, if you say the missing node is say 74% of the whole output, and then you put 74% across all sectors. But say sector A, actually the trades like 70% with the missing node, sector B 50%. And so then it just scales all these sectors by
Yeah.
a factor.
So they actually more or less trade all of them like 90% with the missing. So it's pretty homogeneous how much they trade across firms. And but maybe if I aggregate it by sector, then it's different. Yeah, thank you, Leah. I will look into this. So to conclude, the last results, it's with regard to aggregate volatility. So again, here is to remind you the equation that we are using, and what changes is just the reconstructed or empirical influence vector. So we do this for Ecuador only. We don't care about validating the model. So we just simulate TFP shocks from a normal mean 0 and variance 0.3. And you can see here the growth rates of TFP and the standard deviation. So using the empirical influence vector, we get a GDP volatility of 6.5%, whereas the reconstructed one is 20.5%, which is huge. And so to investigate this, we look at the role of the proxy sector in aggregate volatility. And so we look at the share of its share the share of the variance of the proxy node and of all the other firms. And indeed, the share of the variance of the proxy node is 91%, whereas all the other firms only 8%. And so if you discharge the proxy node, you get still a higher GDP volatility, but way more in line. So to conclude and sum up, so we can recover well the multipliers and the power law exponent of the weight distribution. However, we perform rather bad, at reconstructing the technical and allocation coefficients and in predicting the growth rates of firms' revenues, and especially for FACSET. This is mostly due to the data imputation procedure and a likely misspecified model. So aggregate volatility, we just saw, it's overestimated. And there are huge problems in reconstructing the firm level input-output table for FACSET due to missing data and therefore data imputation, and especially a lot of differences in national accounts and firm level financial statements. And with this, I leave time for questions.
So I think you're being a little hard on yourself, and FactSet is really missing most of the economy. And okay, you may have 26% of the revenues, but it's missing 97% of the links, and you don't have the weights. So you're really, you had a little picture where you showed the jigsaw puzzle. You have only a few pieces in the jigsaw puzzle, and you're trying to guess at the whole rest of it. So and you set up your Ecuador test to match FactSet, which was a great thing to do. But you can imagine lots of other problems where you're not missing 97%, you're missing 20% or something. So it might be, or 10%. So it might be worth doing some other test problems where you just knock out a much smaller fraction of the economy, in which case you'd hope you do a whole lot better. Because you were really trying for a really hard problem.
Yeah, indeed, I did that, and I need to compute the metrics and compare it. Yeah.
Yeah, and the way when you ended, we couldn't do all these things. Well, it's not an either or. There's perfect at one end and absolutely random at the other end, and you were doing better than random, right? The pictures you were getting while there were still really big errors, it was, for some purposes, it would still be better than nothing. And so anyway,
Yeah, so indeed,
don't be too hard on yourself.
yeah, but so indeed, one thing is that I want to check as additional tests is like whether if you use just like an ARIMA model for predicting revenues, then you actually are worse or better than what we do.
Maybe I can just make one more follow-up question or comment. So when you're computing the shocks, I mean, this isn't your biggest problem, but you're computing the shocks, use a Cobb-Douglas function with this Acemoglu model to estimate that. Well, from our paper with COVID, we know that if we had used Cobb-Douglas production function, it would have been horrible. Our results would have been ridiculous.
Yeah.
And it was really essential that we actually do something about the real production function because we queried industry experts, find out the essential inputs of each industry. And so I think that's another thing to think about is whether, because it's kind of crazy to just put Cobb-Douglas on everything. It's one thing if it's just labor and versus capital, but here you're really talking about goods, and it's not like if you're making steel, you can't just substitute coke for iron. That's Leontief. And so it might be worth thinking about that. You could even maybe use some of the stuff we learned in that paper to understand the essential non-substitutable inputs that are really hard and just can't be substituted at all. So that would, which is probably most of them.
Yeah.
I think Cobb-Douglas is very,
Yeah.
I mean, it's probably okay for labor versus capital for some purposes, but that's about it. And also, if you look at Jose's work, I mean, they showed that the Cobb-Douglas function has, and where they're also shocking the economy, has completely unrealistic properties. So, that'd be another. I mean, you did get within a couple of percent.
Yeah,
so it's not terrible.
Because that's because like we are simulating TFP shocks, and then the only thing that changes is the influence factor. So you then don't have these problems about a realistic model that much.
I see.
Yeah.
Yeah, she's comparing Cobb-Douglas with Cobb-Douglas.
Yeah.
So
Right.
But if I had to do this exercise with FactSet, then definitely.
Yeah.
So thanks for the talk. A clarifying question to start. Your reconstruction is an ensemble set, right?
Yeah.
So what were all the results we were looking at? Were those just one realization of the ensemble, or did you do some kind of averaging to get the weights?
So that's the expected.
They're the expected weights.
Yeah.
Okay.
Yeah.
Gotcha.
Yeah.
You could. So then from the way that the ensemble is constructed, do you also know the variation of those weights?
So you can get an upper and lower bound. I didn't discuss it here, but then basically I think around 40% of the weights follow within 50% confidence interval.
Okay.
Yeah.
Cool. And then the second part is I'm curious specifically about the weights that are getting assigned to the links to and from the proxy node. What do those look like? Did you break those out to just see what they look like, or do you know from the model what they are?
So for FactSet, you get that basically those, so that the allocation coefficients are 0.9 for all the firms and the proxy node. And similarly, the technical coefficients are 0.9. Whereas like in Ecuador, it's way more heterogeneous.
Okay.
So most of the results you showed were related to distribution. So you seem to get the distributions right, but that doesn't tell you whether you get the weights in the right location. So the graph where you showed weights versus empirical versus expected, that was more informative, but there was a blob there, so you didn't know whether. So one thing you would do with these weights is, for example, if you know all the weights in the network, and you were doing something related to some policy related to that economy, you would be focusing on the largest weights. So I identify the skeleton, which is the most important in each sector, so on. And so, but that's not taking expectations, that's taking the largest from a given set of random variables. So you might want to look at that to see whether when you look at empirical versus simulated weights, but whether the largest ones are in the same places.
And the correct, yeah.
And whether the skeleton would be the same. If you take like the 10% biggest, you get a similar picture, or it's just that the distributions are the same, but they're shuffled and they're not in the right place.
Yeah.
From the sector graph with colors, it seemed that at least sector-wise, they are roughly in the right place.
Yeah.
But firm-wise, I don't know. I think that could be a
So maybe a heat map of the adjacency matrix would be some.
Yeah, or-
to visualize. Yeah.
heat map or something.
Thank you.
Oh, sorry.
Go ahead.
I did wonder whether some better sectoral data could help a lot. Because there is presumably some meso-level structure in this, that within sectors, there's more trading within sectors than out of sectors. And also that, I noticed on some of the graphs, like, some of the sectors did better than others, and wholesale and distribution looked like it sort of stood out as a different one, which is an odd sector because it's not actually the same as like aerospace or agriculture or whatever. It's everybody stuff, trading through. So I wonder if any data that could help you capture that kind of meso-level structure might help. And I also wondered whether, because of the assumptions about how final demand was being calculated, whether that was rippling through in some funny ways.
That is definitely rippling through for sure, because like some firms in one sector might not sell to final demand at all, whereas maybe the input-output table would hint that it does. I don't know of any data that
I'm
would
not sure what data
help.
would help, but it's more.
No, I wonder whether, again, because of course these are big firms, publicly listed, so their production is scattered all around the globe. So I could not take.
Categorization by sector can be quite funny. Sometimes the way they're categorized is a bit arbitrary.
The biggest problem is that the way they do accounting when firms file their reports versus the input-output tables are different, and it makes it difficult to compare certain things, and that gap can be really quite big.
Yeah, indeed. If you compare revenues by sectors, they're completely off. And
we've been kind of thinking about, is there some way to patch this so that we just have some empirical rule, like in this sector you do it this way, in this sector you do it that way, or whatever. But this is an ugly open problem.
Yeah, and the connection back to final demand then becomes problematic.
I was wondering if there are certainly some firms on which we are doing much better than others at the reconstruction. We talked about, and you showed us that graph where the sector of the firm seems to matter a lot as to how, with respect to how well we seem to be doing. But also, are there other metrics that we can see if there's a correlation with how well you're doing and certain other metrics? Like maybe we are doing really well on high degree firms, maybe we are doing really well on more central firms, something like that, something to understand where where we're doing well and where we are not. Is that something you've thought about or you have?
No, that's actually a good idea, and I will add that further. So I saw that there is some question. So are all nodes connected from one period to the other? So this is just one year. So but yeah, I don't know whether this was referring maybe to the models that I was using, and those are using a static network structure.
Just
go ahead.
Could you just go back to the slide where we saw the straight lines of sectors? I think it was.
So for the revenues growth rate?
Yeah. Do you think it's interesting in some way that most of the dots here seem to be below, between the x equals y and the 0 and the x-axis? We're not overestimating sort of, magnitude-wise the predicted growth rate. Is that interesting in some way?
So that we tend to underestimate in both cases.
In the magnitude in both cases, right?
So I think
Seems to be like a systematic bias, right?
the first thought, I would say that it might be due to the fact that we tend to underestimate also the output multiplier, which then influences, Okay,
Do you think that your model gives insight about the country because it's like it's a small country? Could we reuse this in? Like, do you think that the model gives insights because of the country size or the way that the economics works inside of the country? Like, if it would be a country with a similar size, but depending a lot of business with other countries, do you think that you could have a similar insights? Does it make sense?
I'm not.
I think just my guess is that like Ecuador has oil is the most important industry, right? Not
Quite. Yeah, I
okay,
think
well, but it's gonna, I think it's gonna depend more on the basic characteristics of the economy, like, is it a petrostate, are they manufacturing? Because if you just look at like the spectrum of output multipliers, you see at a glance that China has a big manufacturing economy and so on, just from looking at some measures like that. So I think,
so there are some differences across countries. There are also some similarities, like in related work that we are doing. We are looking at like differences of input-output networks across countries, and there are also some similarities in the structure of the production network. Strikingly, like between Hungary and.
But you know, maybe just following up on that, one thing that goes back to my other comment of doing experiments where you don't remove very much and you see if you can recover that. Like the Ecuadorian government, they may know that they're missing some stuff. And they might want to say, okay, can we use your method to fill in the stuff we're missing, which might be a few percent.
Yeah, so they're missing, I think, 60% of the labor force in the economy.
Because of the shadow economy. Yeah. So, okay, that's still less challenging than what you did. And a lot of countries are just missing a few percent from the shadow economy or smaller percentages. So that, you should, in other words, you have a hammer, you might go look for some other nails to hit than the one you hit, because you hit like the hardest one.
And maybe even looking at sort of if there's a trend of which nodes, which kind of firms we seem to be doing better at, it might be a way to tell, I don't know, governments, firms, whoever's collecting this kind of data, what we need to look for that we are bad at predicting, right? If there's like a limited amount of things that they can look at, what sectors should you focus on that we can't predict with our method, or we are bad at predicting with our method? If there are some correlations that I don't know that would help in data collection in the future.
Okay,
If that makes sense, I don't know if what I'm saying seems to make sense.
I think, thank you, But there are, that's different, but it's 3, so I don't know if people have to leave or otherwise, if there are no other questions, we can finish the seminar.